Latitude Media, podcast at the frontier of climate technology.
I'm Shail Khan, and this is Catalyst.
There's about 200 times less methane by volume than CO2, and one of the major controls on the efficacy of removal is concentration. So that difference in concentration, for one, is just going to make it that much harder to do the atmospheric methane removal.
This week, the extremely challenging, but really quite interesting task of removing 2 ppm methane from the atmosphere.
Catalyst is brought to you by Energy Hub. Facing urgent load growth, it's time for utilities to rally behind VPPs as a solution to diverse grid challenges. Energy Hub helps utilities quickly scale VPPs to manage load growth, maximize the value of renewables, and deliver flexibility at every level of the grid. How do they do it? Energy Hub's software and services enable grid-aware VPP management across distributed resource classes through a best-in-class Edge DERMS platform. Accelerate a reliable, affordable, and decarbonized energy system today at energyhub.com. Artificial intelligence is one of the biggest stories in energy right now, from the AI-based solutions for the grid to the unprecedented load growth caused in part by the AI boom. On December 3rd in Washington, D.C., Latitude Media is bringing together a range of experts for Transition AI 2024, a one-day conference on the AI energy nexus. We'll have networking, panels, a workshop, and technical presentations, and our podcast listeners get a 10% discount off their tickets. Use the code LMPODS10 when you check out. Head on over to latitudemedia.com/events or click the link in the show notes to see the full agenda and register for Transition AI 2024.
I'm Shail Khan. I invest in revolutionary climate technologies at Energy Impact Partners. Welcome. All right, so I think I've said this before, but I sometimes think about greenhouse gas awareness like dominoes of recognition. The world wakes up to the challenge of one greenhouse gas, and then the next, and then the next, in descending order of importance from the perspective of global warming impact. So we collectively, for good reason, focused first predominantly on CO2 mitigation, and then more and more attention has been paid to methane mitigation over recent years. And then I think the next domino to fall is going to be nitrous oxide, because that's the next most important greenhouse gas. But of course, I've been talking just now about mitigation. So what about removal? CO2 removal, or CDR, carbon dioxide removal, has definitely become a thing over the past few years. There's been a burgeoning of interest and funding and startups and research and all sorts of things. So why not methane removal next? Well, the challenge will be fairly obvious to most of you. It's concentration. Methane's atmospheric concentration is about 200x lower than CO2. We're in the 400ths of parts per million in the atmosphere for CO2 and about 2 ppm for methane. So removing the methane is going to be much, much harder, or at least much, much more expensive if we're doing it the same way. But there are a few things about it that are interesting to me. First, obviously, because the global warming potential of methane is significantly higher, 80x on a 20-year basis, for example, you remove 1 ton of methane has a much bigger impact on warming than removing a ton of CO2. So you don't need to remove as much to have the same impact. Second, there are semi-concentrated sources of methane with a higher ppm, and some folks are already working on how to remove methane from those more highly concentrated sources. And finally, with methane, there is one key difference, which is that you can oxidize it. You can turn it into CO2 rather than just capturing the gas and finding a place to sequester it, which is a big advantage relative to what you need to do to remove CO2 from the atmosphere. Anyway, it's still at the very far corners of the world's attention, but I find it really interesting. And there's a great new report laying it all out, published by the National Academy of Sciences. Dr. Gabrielle Dreyfus, who's our guest today, is the chair of the committee that published that report. So I brought her on to talk through it and introduce us to the wild new world of atmospheric methane removal. Here's Gabrielle. Gabrielle, welcome.
Thanks for having me. It's great to be here.
I'm very excited to talk about atmospheric methane removal. I think it's a topic that I've been sort of like waiting for the right opportunity to cover, because it seems like it's sort of right over the frontier of the types of things people in my world talk about regularly. And I love that you guys put together this big, comprehensive compendium of a report on what is an extremely emergent space. I think let's start by making sure we're clear on what we are going to be talking about, because we are talking about atmospheric methane removal. And that atmospheric word is important because, as you pointed out to me, there's a big distinction in terms of available technologies and companies for that matter. If you're talking about atmospheric methane removal versus, I don't know, semi-point source, whatever you might call it. So draw that distinction for me.
Yeah, no, this is a really important point to make because the report we just put out was specifically a research agenda for the atmospheric methane removal component. When we're talking about atmospheric methane here, we're talking about methane in the free atmosphere. So that's the really, really dilute. It's basically approaching 2 parts per million. So 2 molecules for every million molecules of air. And there are lots of sources of methane that are a lot more concentration than that. So there's already methane capture happening at, for example, landfills. And you have these other areas where technologies are being developed to deal with dilute, but not atmospheric level dilute methane. And so the point of the report... Exactly. Dairy barns is a good example.
Right. Coal bed methane. Other places where you've got... It's not exactly like carbon capture in a flue stack, but it's also not 2 ppm.
Exactly. That's exactly right.
Okay. And so you're saying basically there is a bunch of stuff happening there. But what you wanted to look at is the area where presumably then there is a lot less happening, which is removing 2 ppm methane from the atmosphere.
That's right. So the report specifically is asking us to look at this harder technology of removing methane at this ultra dilute atmospheric level of 2 parts per million. And I think as we continue this conversation, it's useful to have a differentiation between the atmospheric removal technologies and their applications at the different concentration levels, because some of the technologies that we're going to be talking about may already have lab-based or pre-commercial or even commercial applications at that dairy barn or coal mine shaft, but not yet at the 2 ppm level. And so that's where this, as you said, this is a very much an emerging area of research.
So I guess the obvious question before we really dive into it is like, why, right? It seems on its face, we know how, and we're going to talk a little bit about, I think, the contrast between atmospheric methane removal and atmospheric carbon removal. But, on its face, we know it's hard to do direct air capture or other forms of atmospheric carbon removal. And you have a couple hundred times the ppm to deal with there versus 2 ppm methane. What is the thinking around, like, just at a most basic level, are we really going to need to do this? And do we really believe it could possibly be reasonably economically affordable? Like, we'll talk about the details, but from a high level, is your view this is likely in our future?
It's a really good question, and one that especially people who approach this thinking, well, methane is short-lived. It doesn't behave the same way as CO2 in the atmosphere, where CO2 builds up because it lasts so long. Methane, because it has a shorter lifetime, this idea is it will take care of itself. And that is true if those methane sources turn off. But here's the rub. Human sources of methane, there are some that we have mitigation alternatives for. And when we talk about hard to abate sectors for carbon dioxide, there are also hard to abate sectors for anthropogenic methane sources that we don't have good mitigation options for, that will continue to emit into the future. And on top of that, about 35%, about a third of current emissions to the atmosphere are from natural sources of methane, and these are expected to increase their emissions in a warmer and wetter world, and we have no mitigation technologies currently available today to deal with these generally diffuse and low concentration sources, like recently a big surge of these emissions in the tropical wetlands, for example.
Right. Okay, so we're going to talk about what are the possible atmospheric methane removal technologies that we could run down. First, I think people listening, I'm guessing, are pretty familiar with carbon removal because carbon removal has gained a fair amount of attention over the past few years. So let's do a quick compare and contrast as we think about removing atmospheric methane versus removing atmospheric carbon. What do you think of as being we mentioned the difference in ppm, the concentration of the atmosphere, obviously huge difference there. What do you think of as the other core distinctions we should draw as we start to look at atmospheric methane removal?
Yeah, so especially for people who are thinking about carbon dioxide removal, that concentration difference is huge. There's about 200 times less methane by volume than CO2. And one of the major controls on the efficacy of removal is concentration. So that difference in concentration, for one, is just going to make it that much harder to do the atmospheric methane removal. We also just touched on these issues of lifetime, where CO2, because it has this century scale lifetime in the atmosphere, builds up. Methane, shorter lifetime. It is on the order of 10 years. There's this self-cleaning effect of methane in the atmosphere, and that's actually a really important and kind of cool aspect, which is that methane emissions have an effect on methane lifetime. Because the amount of detergent in the atmosphere that is what reacts, that removes the methane, is primarily the hydroxyl radical, OH. There's also a small component of chlorine atom, and there's also a small amount of exchange with soils and ecosystems that will eat methane. And it's in particular the availability of the hydroxyl radical that is the main control on methane lifetime. And so if you increase methane and keep the hydroxyl radical the same, you extend methane lifetime. But conversely, and this is the cool part, if we are successful with methane mitigation, controlling those human sources of methane that we know how to control, so oil and gas leakage, no excuse for that. That is technically fixable. If we reduce those methane sources, that means that there's less methane for the hydroxyl to react with, and the methane lifetime should go down. So this is a really cool feature, and one of the reasons that mitigation really is so important to do first is if the game here is reducing methane lifetime, reducing methane emissions gets you that.
Yeah, it's like there's a version of a positive feedback loop you could introduce there.
Exactly.
That's interesting. To a first order, one way that I've thought about it, and you could tell me if I'm missing something here, is that in terms of the sort of challenge of removing atmospheric methane, you've got 200x less concentration, plus or minus, versus CO2 in the atmosphere. But methane has, if you're looking at like a 20-year basis, 80x the global warming potential. So there's like a ratio there that makes it still seem harder, right? But not 200x harder. It's like 200 divided by 80 harder. So a little more than twice as hard.
So in terms of impact aspect, so that when you introduce that global warming potential, that 80 to 90 times more potent over a 20-year lifetime, yes, if you're talking about climate impact, the amount of methane that you have to remove for a comparable climate impact to CO2, when we're talking about gigatons of CO2 removal, we're talking about megatons of methane removal for a comparable scale impact. But there's another piece, though, for that to be comparable that relates back again to lifetime, which is because that methane would have gone away eventually over time, to maintain that temperature impact over time, you actually need to continue to remove the methane, not at the original scale, but there's this concept of effective methane removal. So you have your initial large removal and you have to continue to remove a tail if you want to have a comparable temperature impact to CO2 because of that lifetime difference.
Yeah, okay. That's an interesting point. Okay, and then the other thing for me that is, I think, an important distinction between CO2 removal and methane removal, before we get to the methane removal technologies, is with CO2 removal, basically to remove CO2 from the atmosphere, you got to capture it and sequester it permanently somewhere. You got to put it underground or something like that. But the interesting thing about most of methane removal approaches, including the ones that are at coal beds or wherever, you don't have to capture a gas and then find a place to sequester it underground. You're just oxidizing it, really, and you're turning it into CO2, which makes sense when you appreciate the global warming potential difference between the two. You get your 80x reduction in global warming potential. And so just the ability not to deal with sequestration is actually a pretty big advantage in my mind of methane oxidation as a form of methane removal.
Absolutely. And the really important premise here is to know that almost all of that methane, business as usual, would convert to CO2 anyway. So as soon as you're releasing methane to the atmosphere, if it's a fossil source methane, then yes, that CO2 that it's eventually converted to is additional CO2 that's being added to the atmosphere, but the potency is significantly lower. So 80 to 90 times over 20 years, about 30 times over 100 years. And so from a climate impact perspective, that's a huge win. But if what you're dealing with is a kind of biogenic carbon cycling, then that's essentially you're just, accelerating that carbon cycle, right? It's not a net carbon addition to the atmosphere.
Catalyst is brought to you by Energy Hub. Energy Hub unlocks the power of VPPs to deliver flexibility to the grid. How do they do it? By enrolling DERs in customer-centric flexibility programs and using AI-driven optimizations across devices to shape desired load profiles. Energy Hub has more gigawatts under management than any other edge DERMS on the market, and they have a proven track record of building high-performing VPPs in record time. Working with more than 70 utility clients across North America, Energy Hub delivers reliable flexibility at every level of the grid. Click the link in the show notes to learn more or go to energyhub.com. Where are you going to be on December 3rd? I know where I'm going to be. I'm going to be in Washington, D.C. at Transition AI 2024. That's when Latitude Media is offering the chance to hear from experts on the front lines of AI deployment in the energy sector. Transition AI 2024 is our one-day in-person event, again in Washington, D.C. It addresses both sides of the AI energy nexus, the challenges AI energy demand poses for the grid, and the wide opportunities to help climate solutions. This is our third event, and we brought together a really great lineup for this year. It includes Meta's former Director of Energy Strategy, Peter Freed, DOE's Chief AI Officer, Helena Fu, Paige Crahan, who heads up Tapestry, Google X's moonshot for the grid, and AES Chief Product Officer, Chris Shelton, plus many more. And our podcast listeners get a 10% discount. Use the code LMPODS10, that's Latitude Media, LMPODS10, when you check out. See the full agenda and register today at latitudemedia.com/events, or just click the link in the show notes. I will be there. I hope to see you there. Transition AI 2024.
Okay, so let's get to it then. Say we want to remove methane from the atmosphere. The report that you guys put together laid out a bunch of different possible technologies. So I want to talk through each of them individually, talk about the premise, and then kind of state of the art, like how far down the technology maturity road are we? Starting with methane reactors. So describe what a methane reactor is and does, and how far are we from building one?
Yeah, so methane reactors are essentially, methane reactors in a box is what I like to think of them. So they're physically bounded systems. And so they are partially closed in the sense that the reactions are taking place in a closed environment, but air and energy is able to move through. And so they are intended to oxidize methane inside the bounded system. And so they're most similar to some of the direct air capture kinds of conception, right? You bring air in to a system that has some kind of catalyst. It could be a thermal catalyst or a biocatalyst or a photocatalyst. Those are all things that are being looked at. Essentially, to your point, the advantage of methane is that carbon-hydrogen bond can be oxidized. Now, you have to add some energy because those bonds are quite stable to break them, but that amount of energy is, this is where you have to put energy in, right? You have to heat the air or heat the catalyst or provide some kind of form of energy to break that bond. You have to move a large volume of air. If you're going to have a megaton scale impact, that's a lot of air that you have to move. But we did some very rough back of the envelope calculations for the study. And when you look at some of the projections for the amount of direct air capture or carbon dioxide removal that some people are projecting, actually, it's a very large volume of air. And if you could, for example, synergistically couple that with some methane removal, you could, for the same volume of air moved, you could also get some of that.
Because I was imagining,
removal,
right? Okay, so I was imagining if you just have a standalone methane reactor taking air and moving it and trying to react, you've got 200x less concentration of methane. So to a first order, you'd have to move 200 times as much air to do this as you would to do the equivalent amount of CO2 capture. And the amount of air that you have to move for direct air capture is already a problem. And the amount of energy you have to use to do that. So it's sort of hard to conceptualize. But that last bit you said is interesting, which I hadn't thought about, which is you could do dual duty at a single system where you were doing direct air capture and methane oxidation in the same system with the same forced air.
In theory, yes.
And right, you just have an extra process step where you're introducing your methane catalyst.
Right.
That's pretty interesting. Where are we in the state of development of methane reactors, atmospheric methane reactors? I mean, presumably this stuff is the closest to what is already being developed for those more concentrated locations, right?
Exactly. So there are commercial and research reactors that can work down to approximately 1,000 parts per million. And so you have thermal oxidizers already in coal mine vent air, and you have some research reactors being applied in dairy barns where cows, of course, enteric fermentation, they spend time in there. It's inside a confined space. You can get an increase in the methane in the air to a high enough level that some of these these concepts are being tested in dairy barns.
And then beyond that, is anybody yet attempting to just do it with atmospheric concentration?
Not to our knowledge. This was one of the key features of the report, and the reason that as part of doing the report, we actually commissioned 4 studies is because this is still such a new concept that at that 2 ppm level, there is very, very, very little available information on that. We were not aware of these methane reactor type approaches being working at 2 ppm. Again, there's that about 1,000 ppm kind of limit that is our current understanding.
Okay, so that one is probably the most obvious category in my mind. Just build a machine that oxidizes methane from the atmosphere. Let's talk about the next category in the report, which is methane concentrators.
Yeah, so methane concentrators are devices that would separate or enrich methane with some degree of selectivity. And the idea of the methane concentrator is that it would not necessarily do the methane removal itself, but it could be enabling for a methane reactor, for example, to increase its efficacy. So if the stream of air going into the methane reactor was already pre-concentrated in methane at a level that could improve the economics, the technical viability of that unit. And the challenge here, and again, this is getting back to that analogy with CO2, is unlike CO2, which is sticky in the sense that it's amenable to acid-base chemistry. There are ways that you can grab a hold of a CO2. Methane doesn't really have the same properties. It is symmetric. It doesn't have acid-base chemistry. It's small. It's similarly in size to N2. So there's a lot of N2 in air. So in terms of size separation or chemical separation, there's not an easy way to separate it out. And so this one is identified in the report really as where breakthrough there hasn't been a lot of attention to this technology approach. And so this is where if someone could come up with a really clever way to do a separation, it could be a very important enabling technology for atmospheric methane removal. But we are not currently aware of atmospheric methane concentrators that are able to enhance methane from an ultra-dilute 2 ppm to a higher level of concentration.
So would it be right to think about this one as it's like a front end or an enabling category for a methane reactor?
Primarily,
the methane
yes.
concentration in and of itself doesn't do anything for you, but if you can cheaply concentrate methane, maybe it alleviates some of the burden on the reactor.
Exactly. So that's the main way that this is being thought about. And there may be, if there's like a use or capture case, there may be other uses for it, but that's primarily the way in which we were considering this.
Okay, so let's move on to some of the other more novel, or at least like less similar to what we're seeing in CO2 categories, starting with surface treatments.
Yeah, so now we're moving from these closed or partially closed type technologies into open system type technologies. And the idea of a surface treatment is you could take some of that biocatalyst or thermocatalyst, or in particular a photocatalyst, right? If you're having this outside that you might use in a methane reactor, and using it to coat surfaces, and in particular surfaces that have high exposure to sunlight and to air. So if you think about a wind turbine blade, that's moving a lot through the air. So rather than you use fans to move air through a box, the idea is to take that catalyst that would have been in the box and put it on something that is already moving in contact with a lot of air, just again to increase the efficacy through that contact. And so this is not a technology that does not currently exist for methane at 2 ppm. There have been some surface coatings proposed for reacting other chemical species in air. And so this is essentially a technology by analogy that in theory, you could have a photocatalyst, but it would have to, this is where some of the research questions that we're going to get to in the report, it's just what some of this is where getting like some of the material science, right? What is it about the catalyst that is going to make it be effective in ambient UV conditions at ambient temperature?
I've seen a couple of startups proposing this exact thing: surface treatment with some kind of spray-on catalyst that you put either on wind turbine blades or something else that, in principle, would oxidize methane in the atmosphere. I think it still seems clearly very early in terms of proving it out. And this one is one where like you would have this, you'd get into the realm of some of the similar MRV challenges, I think, that you end up with certain forms of carbon dioxide removal too, which is like you put your surface treatment catalyst on your wind turbine blade, and then how do you know how much methane you have actually removed? Can you measure that? Do you have to model it? Like, it starts to get a little complicated there.
Really good question. So yeah, a big piece of the research agenda in the report is the specific research needed around the MRV for each of these types of technologies. Like the methane reactor is it's a lot easier in the sense that you could put some kind of methane monitoring at the front end and at the back end, and you'd probably be able to detect the change. Whereas some of these open system, the surface treatment is the first of the open system technologies we're discussing. The open systems are where we have the greatest need and limited current technologies to really have the robust MRV.
Okay, so moving on to category 4 out of 5 then, ecosystem uptake enhancement. This one's interesting.
Yeah, so this one is really interesting. It's the one where the idea is that through some kind of amendment to, for example, a cropland, or through a change in practice, right? We know from soil carbon sequestration that, tilling versus no tilling, the way that the soil conditions are changed, you can affect the microbial activity. And we know that in soils, but also really cool, there are new studies coming out about what's happening on on tree leaves and woody surfaces. You have a whole ecosystem of microbes, some of which are methanogens. So these are ones that will generate methane. This is, part of why in swamps we have swamp gas, that when you are in a low oxygen environment, you have microbes that will produce methane. But depending on the availability of so that there are going to be certain like copper and other things that are in the soil that are used by microbes that eat the methane, the methanotrophs. So by changing the oxic environment, by changing the availability of different micronutrients, there's this idea that you can encourage the net consumption of methane in these ecosystems over the net generation. And so this is where there's some really interesting new work, and that it's just very underexplored at the moment. And I don't want to oversell it. This is challenging. The microbes that eat methane, it's a hard life. Eating methane is, it's not the most energetic food. And so to create, and this is where you're, trying to manipulate a system to encourage it, like how much you could get these to flourish is what the constraints are on those systems. These are still all very active research questions, but there's also the possibility that small changes in like farmer practices, that could also, increase the net methane flux, reduce the net methane flux to the atmosphere over large areas, right? It doesn't have to be huge if it's over a large area. So this is why it's a really, I think, particularly interesting and intriguing technology option.
So maybe you answered this, but one of my questions was just going to be like, what might this look like practically? So you're saying some farmer changes, or their input changes? Like what types of things might we have to do to enable this?
Yeah, so there's this idea of amendments, so things like biochar or other substrates that you could add to the soils that would essentially change some of those soil conditions that make the methane-eating microbes happier and more able to compete more effectively. So there's a set of potential amendment approaches. But then again, because some of that activity has to do with the state of water and air oxic conditions, it could be how the soil, right, how a farmer till versus no till. There's also management practices that could be different that could affect that balance. And so there's really interesting work here just to look at maybe some of the practices that farmers are already using in certain conditions may have promise for this, for essentially enhancing that ecosystem uptake.
Fascinating. I guess that's their sort of, right, this is the regenerative ag-like equivalent here.
It is, yeah. It fits on that. One of the things, of course, in all of these, and we can get to these, is understanding that these are systems where there's other nutrient cycling processes. You have to be really careful that you're not going to tip the system to increase, for example, nitrous oxide production. This is one of the things we talk about, for example, methane from rice farming, where you have flooding or not, and how that's used. This is where there's really important research questions to better understand how interventions in these systems really, what the net effects are, and to try to optimize to the desired effects, which could be net ecosystem beneficial, but also how to minimize undesirable effects on nutrient cycling, nitrous oxide, et cetera.
Do we have a sense of how? I mean, I guess if you do this at global scale, it would have a huge impact. But like, what's the potential of this category?
Yeah, so this is one where, again, we made very rough estimates because, again, there's very little data available. Again, this is such a new area of research looking specifically at how modifications via amendment or management on methane specifically. So we don't have great numbers right now. But this is one that could potentially have, I think we don't use this analogy in the report, but I think it's one that's widely used in the climate space. This could be one of those pieces of silver buckshot, right? It's not going to be solving the whole methane challenge, but it could be significant in addressing some of the opportunity for managing methane emissions.
Okay, on to the last category described in the report, which is atmospheric oxidation enhancement, which is another one that is sort of a unique to methane opportunity that you again, as we discussed before, like this is the thing that isn't available to us with CO2.
That's right. So the atmospheric oxidation enhancement is taking advantage of the fact, as we talked about earlier, that there is this detergent natural oxidation in the atmosphere. The hydroxyl radical is the primary source. There's also chloride. And that if you could increase the oxidative capacity of the atmosphere, you could reduce methane lifetime. And so I'm going to go back again and just repeat what we talked about at the beginning, which is this cool feature that by reducing methane itself emissions, you have this reduction in methane lifetime for the same amount of hydroxyl radical. But these interventions would be specifically looking at increasing, for example, the availability of the hydroxyl radical or of chloride. So in these cases, similar to the idea of adding amendments in the ecosystem uptake enhancement, there would be an amendment, something added to the atmosphere that would stimulate either hydroxyl production or chloride availability, and that thereby increase the oxidative capacity of the atmosphere and reduce the methane lifetime. But similar to what we were just talking about with the ecosystem uptake, there's other things going on in the atmosphere, atmospheric chemistry and processes. And so this is one where, again, there's a lot of MRV needs and a lot of research questions to better understand what the other reactions that might happen in the atmosphere. It's not just methane and hydroxyl radical out there. And what the consequences of an addition of the kinds of amendments that could increase the hydroxyl radical or chloride, what other consequences those might have on other climate forcers or on clouds. There's some really important questions, and the amount of modeling, so atmospheric chemistry modeling and observations are very limited at this point.
Okay, so we've covered our categories. It's clearly very early, but a bunch of interesting possibilities to run down. I guess just to wrap it up, what do you hope to see over the next few years? What are the biggest gaps that we need to fill? Obviously, there's more opportunity for R&D funding and so on. What's on your wish list?
Yeah, so as we were talking about, this is still really early stages. And I think just to get to what you were alluding to earlier with these technologies is that atmospheric methane removal, we're still just talking about just a research agenda. We're not even talking about a field yet. This is really new. All of at the 2 ppm level, all of those 5 technologies we just talked through are at very early technology readiness levels. And so that's why the main recommendation of the National Academy's report is actually to divide this into a multi-phased assessment. And so that this would be really a first phase assessment where we've identified a number of foundational research questions that need to be answered that would enable a more robust assessment to get to some of your quantification questions, like what's the potential? I'm trying to avoid answering here. It's like, we don't know. We don't have enough data to provide a robust, reliable estimate on the potential of these technologies. And so the research questions, so the report sets out 5 research areas with specific research questions that are in the materials science, in the biological sciences, and the social sciences to understand. Again, this is any kind of climate intervention technology. It's really important to have a better understanding of how people might engage with the research, what kind of governance questions. We already brought up MRV as being super important. Then there's the question of what's the role of markets? All really critical questions, and that we've spelled out in the report need specific research needs that would allow a more robust assessment. And what we're hoping, again, because of the timeline here, we want to understand this better, is that there would be funding available within a year so that we could have research start very quickly so that we could actually do a follow-up second assessment in about 3 to 5 years to do a better job of answering some of those questions that you've been asking.
All right, Gabrielle, super interesting. Like I said, I love something that feels like the world hasn't quite woken up to it yet, but is going to start at least talking about it and hopefully learning about it over the coming years. So hopefully we're just a little bit ahead of the curve, but appreciate that you put all this work into laying out the possibilities and taking the time to talk through it with me.
I really appreciate your time. I think one of the things that may or may not have come through as we were talking through this, and I think I hinted at this a little bit, is the value of this being interdisciplinary research from the get-go. Because this is so new, we have an opportunity to really intentionally work with it through the, understanding how engagement works, to understand how people think about this type of technology and design science that is both better science, but also better understood. I think that there are real risks in these types of technologies of getting ahead of understanding. And so I really want to emphasize that there's real technology potential around this, but there's also real interdisciplinary science and communications. There's just a lot of, I like to see this as a greenfield opportunity.
Well, thank you again. Dr. Gabrielle Dreyfus is the chief scientist at the Institute for Sustainable Governance and Development and the lead author of a great report on atmospheric methane removal that was just published by the National Academy of Sciences. This show is a production of Latitude Media. You can head over to latitudemedia.com for links to today's topics. Latitude is supported by Prelude Ventures. Prelude backs visionaries accelerating climate innovation that will reshape the global economy for the betterment of people and planet. Learn more at preludeventures.com. This episode was produced by Daniel Waldorf, mixing by Roy Campanella and Sean Marquand, theme song by Sean Marquand. I'm Shail Khan, and this is Catalyst.